why. Um, I mean, I don't record when I should, and I record when I shouldn't. So I wish someone would tell me not to record when we're doing the Kahoot. But thanks for reminding me. Okay, so these rectifiers, diode rectifiers, we looked at them in electronic circuits, but there's much more to them than the basic circuits that we looked at in electronic circuits. And that gives you an idea of how deep you can get into these circuits and into the theories if you decide to go into graduate studies. I mean, you can actually do a PhD on basically improving rectifiers and making them more efficient. So this just gives you like the things that we looked at in the previous courses, in the first year courses. They were basically just the tip of the iceberg. You can dig quite deep into them. Yes, Imran.
I was just curious to know, so because this power electronics, it's a relatively new field, did you learn about all this in school or after that?
In school and after. So we had two power electronic courses, one in bachelor's and the other one was I did another one in my master's, and I did a self-study in PhD. You could take the master one as an elective course as well. So I'm actually thinking of maybe creating a course, like an elective course that we could offer both to bachelor's and like undergrad and grad students. But this is new, but it's not that new. It's like these things, like these concepts, they have been around since the 60s and 70s, right? Because 60s and 70s were when the power electronic industry started to basically take off. So they've been around for quite some time. So at least like you'll see 2 or 3 generations of engineers who are familiar with these concepts, but their applications are widening, right? And again, like this is the tip of the iceberg. So even though we are looking at all sorts of loads and circuits, we haven't even touched the control side yet. So we're just looking at the devices and how they would behave, but we haven't looked at how to control them. So in like more advanced power electronic courses, you learn about how to actually do a control. So if you're using one of these devices to control your electric vehicle, how do you control the speed? How do you control the torque? Stuff like that. How do you do regenerative braking, right? So those are more advanced topics. But anyway, so on diode rectifiers, we looked at a case where, like cases where we had purely resistive loads, and we saw that if you have a purely resistive load, the current on the supply will be sinusoidal, right? I mean, you get a rectified current on the output, but the current here won't be affected. So there won't be any harmonics that you inject back into the grid, because the current that you're pulling from the grid is this, which is sinusoidal. And it'll be in phase with the voltage as well, because you have a resistive load. Now, what happens when we add an inductor into the load is that perfectly sinusoidal current will become something like this. So this is not sinusoidal anymore. And what does it mean? If it's not sinusoidal, it means that it'll contain many harmonics. So we are now injecting harmonics back into the grid because the current that we are pulling from the supply is not sinusoidal anymore. So just remember that once the waveform deviates from a sine wave or a cosine wave, I mean, it can have a DC, but once it deviates from this shape, the sinusoidal shape, it means that it contains harmonics. Now, so this is if you have an RL load, a general RL with a supply, a DC supply, and the reason we chose this load is because it resembles most motors, especially DC motors, because that's where you would want to use a rectifier in the industry, right? Most of the time, you want to rectify an AC supply so that you could use it on a motor. And like the inductance in the motor, it doesn't show its effect if you supplied a constant DC current, but the moment the current starts having a bit of a AC component, then the inductor also shows its effect. So we have the LA here as well, and that was the reason we chose this this type of a load. Now, in places where the load is highly inductive, so if you could imagine the load being just a giant inductor, so if you have a really big motor, a really powerful motor, the inductance is much more than the resistance or the E, right? And big inductors, they basically pull a constant current. They do not let the current change. So what would end up happening is that your load would act like a current source. So if you imagine you have a current source for your load, then the current that your input and output voltages and currents would look like this. So notice that the output current is a constant. It's a constant IP, I've called it, right? And it's because the inductor does not let the current change. But and the input is the input voltage is a perfectly sine wave. So the input voltage Vs is a sine wave. Now look at the input current, or the current that we are pulling from the grid. I mean, in this half cycle, we are pulling the current from this side. So the current comes in through D1 and goes back through D2. And on the other half cycle, we are pulling the current this way. So the current that we are pulling from the grid is now coming this way, right? It's coming here and going back here. So the input current is changing direction. I mean, we are still pulling a constant current, but the constant current creates this square wave. And this square wave contains many harmonics. Okay, so this was the output current, this thing, and this is the input current. Now in harmonics, we have many frequencies, but the first frequency is called the fundamental component. So if you write the Fourier series for this square wave, it will contain many sine and cosine waves with different frequencies, but the one that has the fifth component or the fifth harmonic will be a sine or cosine wave that we call the fundamental component. This fundamental component, we call it IS1. Okay, and we want to look at this fundamental component because using the fundamental component, we can define three other indices, if you like, that shows the quality, the performance quality of the rectifier. The first one is called the displacement power factor. The displacement power factor is like a power factor for devices that contain harmonics. So if you have something like a motor or a load that does not change the waveform of the voltage and current, we have something called power factor. But the power factor is the cosine of the phase difference between the current and the voltage in a circuit, right? But if your current is not a sine wave, if your current is, for example, a pulse wave, a square wave, then instead of power factor, we define something called the displacement power factor. I'm going to talk about it in a second. Yes, Paola.
Is there a reason why in this circuit the voltage is a sine wave and the current is a square wave?
Why is that? Well, the source is always a sine wave, right? I mean, the whole purpose of an inductor is to change a sine wave into a square wave, sorry, into a constant. That's the whole purpose of a rectifier. It changes AC into DC. So the input, which is a source voltage, is sinusoidal, is AC. The output, because the load is inductive, will act like a current source. So the output will be a flat DC current, not voltage, but DC current. And if you're creating a constant DC here, it means that your input will change direction. Once these two are switching, your input current is going this way. Once these two do the switching, your input current will change direction and will go this way. And so you get this square wave. Does that answer your question?
And is that because you're assuming like that the L is significantly bigger than the R, or that has no input?
Yeah, it's because this is basically what happens when I have a really big inductance in the load. So if you're using this rectifier to supply a motor has a winding, right? And that winding is like a giant inductor.
Okay, thank you.
So we are exaggerating, but we want to basically, I mean, you will never get something that looks this perfect square, but you might get something that looks like this, but it's close enough, right? Okay, so the displacement power factor, as I said, it's a power factor for places that have harmonics. So if your current or voltage waveform is not perfectly sinusoidal, then the power factor for it, the actual power factor, will be called displacement power factor. Total harmonic distortion is a variable that shows how much harmonic contamination you have in your circuit. So the further you are from a perfectly sine wave, the more harmonics you have in your circuit. And then the power factor is something that includes the harmonic. So if your current or voltage is not a perfect sine wave, your power factor should be modified so that it includes the harmonic component as well. And I'm going to basically show you what each one of these are. So we call the first or the first harmonic of this current, which was the square wave, the fundamental component. The angle that the fundamental component of the current makes with your input voltage. Now, I'm comparing two sine waves now, right? The phase difference is called the displacement angle. So the displacement angle is the angle between the fundamental component of the current in this case, that is not a sine wave, it's a pulse wave, and the voltage. The cosine of this angle is called the displacement power factor. Okay, so we are still using the same equation as before, cosine of phi, but because one of the two variables, in this case the current, is not a sine wave, phi is going to be the difference between its fundamental harmonic, which is a sine wave, and the voltage. Now, the total harmonic distortion comes from this formula. I mean, sometimes the total harmonic distortion is called the harmonic factor, but THD is the industry norm. And it comes from this formula. It's basically the square root of the square root of the current, RMS current, over the RMS of the phase component squared minus 1. And we usually define a THD as a percentage. And then we have the input power factor. So the input power factor is the displacement power factor times this portion, this fraction here. And if you play with the math, you can actually write the power factor as a displacement power factor over root 2 of 1 plus THD squared. So power factor in places where either the voltage or the current is distorted includes the THD component there. Okay. Now, if we didn't have a pulse wave, if the current was sinusoidal, then the THD would have been 0. You wouldn't have any harmonic distortion. And IS1 and IS would have been the same. So in that case, the displacement power factor and the power factor would have been the same. Okay, so in all of the circuits that we looked at, for example, in circuits where we had perfect sine waves, we were actually measuring the displacement power factor, not the power factor. But because we did not have any harmonics, the displacement power factor and the power factor were the same. Okay, now let's look at this in an example. And I think you have, or you are actually studying Fourier analysis, right, in math. Have you already done it, or are you going through it now?
For signals on systems, we're gonna be learning it soon, I think.
Okay, so if you haven't seen it before, have a look at Appendix E. What the Fourier analysis says is that if you have a periodic waveform, so if you have something like this, right, the square waveform, you can basically make this waveform by adding a constant plus an infinite series of sine and cosine waves. So that means that if you add a constant plus a number of sine waves and cosine waves of different frequencies, you eventually will end up with this waveform. And that applies to any periodic waveform. So it could be a sawtooth, it could be anything. It could be a pulse wave, right? And it shows you basically how to calculate these factors. So the A0, the constant, is called the DC. So it's like the average of the waveform. So if you have something that looks like this, the average is 0. So the constant will be 0. And then A1 and A and B, which are the coefficients of the sine wave, the cosine wave and the sine wave, can be calculated from these other formulas. Now let's look at our example and see if we can apply that here. So here I have the rectifier that is supplying a DC motor. So the DC motor is, I'm assuming it to be a highly inductive load. So it's pulling a constant current. So the output current here is constant. Now the output current is constant. That means that the input will be a pulse wave like this. Because in order to provide a constant current on the output, the input needs to switch direction every now and then. So that I get a constant here, right? So it says a single-phase bridge rectifier supplies a very highly inductive load, such as a DC motor, as shown in Figure A. The turns ratio of the transformer is unity, so that means that N1 to N2 is 1. So whatever is the voltage here, it won't be amplified, or it won't be scaled down. You get the exact same voltage on the other side as well. The load is such that the motor draws a ripple-free constant armature current that equals IA. So the current on the output is a constant. It says in here, determine the THD, the total harmonic distortion, the displacement power factor, and the power factor. Remember that these three, in this case, are all are basically variables or measurements that you're asking about the input side. So, I mean, you can define the same thing, THD, displacement power factor, and power factor for the load as well. But here, we are asking these on the input because we want to know how much does this system affect the grid or affect the neighboring loads, right? So we want to know how much is the harmonic contamination, what is the power factor, so how much reactive power you're pulling from the grid, and what is the displacement power factor, etc. So this is just for a DC motor, but in general, any kind of a motor, regardless of whether it's DC or AC, because they contain windings in them, it can be considered as highly inductive loads. Okay. All right. So we know that if the output is to be a constant, if the output current is to be a DC and constant, the input current has to switch. So it'll basically become a square wave like this. Now, this square wave has a fundamental component. So that means that I have to write the Fourier series for a pulse wave. And how do we do that? So using the formulas that I showed you on that appendix, I can write the equation for the Fourier equation for this input current, which is a pulse wave like this. It has a DC or a constant component plus a number of, an infinite series of sine and cosine waves. Now, when you write the equation for these coefficients for AN and BN, you're going to see that for square waves, there are no even coefficients. All the even coefficients will equal 0. Okay, I'll let you guys try that at home, but when you write the equation, you're going to see that all the AN and BN values for N equals even will be 0. So you won't have, for example, A2 or B2. You won't have A4 or B4. They are all 0. So you only have odd coefficients. Now, here I want to find these coefficients. So first I want to find the DC. What is the DC value of this waveform, this square wave? What's the average? If this is a pile of sand and I'm flattening it over this area, what would be the good? So the height will be 0, right? Because this area equals this area. So the average is 0. And when you put it into the formula, you get that as well. So the formula says IDC is 1 over the period. The period here is 2 pi. The integral from 0 to 2 pi of the waveform, which basically means the area under the waveform over the length or the period, 2 pi. So the waveform is IA, and if you do the calculation, you get 0. It's actually, you got to break it into 0 to pi IA plus pi to 2 pi minus IA. But then when you do the calculation, this equals 0. So there's no constant. Now let's see if we can calculate the coefficients of the cosine wave. So the coefficients of the cosine wave comes from this formula. 1 over pi, 0 to 2 pi, is times cosine of n omega t, and we are integrating it with respect to omega t. Again, you can break this into 2 regions. 0 to pi, you have IA cosine n omega t. And then pi to 2 pi, you have minus IA cosine n omega t, right? And when you're integrating, we are integrating with respect to the omega t. So what is the integral of a cosine? Anybody? What is the integral of a cosine? Sine. Yeah, forget the constant. It's just sine theta. So if we place in, if you plug this in, I have 1 over pi. Just gonna bring IA out. So I have 1 over n sine theta, theta from 0 to pi. What is sine of 0? 0. What is sine of pi? Again, 0. So this is 0 minus 1 over n sine theta from pi to 2 pi. Again, both sine of pi and 2 pi are 0 as well. So when you work out this integral, you'll find that all the cosine coefficients are 0 as well. Okay. So when you're writing the Fourier series for a pulse wave like this, you don't get a DC value, the DC is 0, and you won't have any cosine waves. You'll only have sine waves. So if I calculate the coefficient of the sine waves, when you do the integral, the coefficients will be 4 times IA over n pi. What is n? N is basically the harmonic. So here I only have odd harmonics. So that means that when you substitute it back into the equation, you can write the equation for this pulse wave as 4 times IA, so IA is the peak, over pi, times, these are the harmonics. This is the fundamental, or the first harmonic, then the third, the fifth, and so forth. The more of these harmonics you add, the closer your waveform will be to this pulse wave. So now I have the equation for my current with the harmonics. So now I want to find IS1. IS1, or the RMS of it, the RMS value of the fundamental component of the input current. This is the fundamental component, the first harmonic. The peak value is 4IA pi sine omega t. This is the peak. So if you have a sine wave that has a peak, how do you find the RMS? You divide by √2, right? So you can calculate the RMS of the first component by dividing the peak by √2. So the RMS of my first component or first harmonic is 90% of IA. So that means that the fundamental component is actually like this. Where this is 0.9 IA. And what is the RMS of the actual waveform? So what is the RMS of this pulse wave? Anybody? If you work out the RMS, what do you get? Circuits course, C230. If I give you a waveform that looks like this, how do you find the RMS? You square these. So here you get IA squared. The negative when you square it becomes positive as well. So again, IA squared, you add the areas, divide by the period. So I have 2I squared over, this is 2 pi. Over 2 pi, square root of it, you get IA. So the RMS of this waveform is actually IA. If you work out the RMS of this series, you also will find out that it converges to IA. But we already know how to do RMS calculation for square waves. So now I have everything that I need to move forward. So the first component, the first harmonic, the RMS value of it is 90% of IA. The RMS of the current is also IA. Remember that these are the input currents, right? The input of that rectifier. So the total harmonic distortion, I have IA over 0.9 IA squared minus 1. So here I have 48% total harmonic distortion. That means that if you plug this rectifier into the wall to supply a DC motor, you will get about 50% harmonics back into the grid. By standard, these days you cannot have a THD that is more than 5%. So this is 10 times what you're allowed to put back. So what that means is that somehow you have to have a filter here. You can't just plug this into the wall. You have to put a filter. And these filters, sometimes you see them in some devices. You see these cylinders on the wire, on the plug. The cylinders are the filters that filter the harmonic before you plug, for example, the DVD player or the home theater into the wall. That's to bring down the THD to less than 5%, which is what is required by the code. So now I have the THD. Look at the first component, or the fundamental component of the current. What is the angle that it's making with the voltage? What is the phase angle difference? Anybody? 0. So the phase angle is 0. If the phase angle is 0, the displacement power factor, which is cosine of phi, is 1. So the displacement power factor is 1, but the actual power factor that also has the harmonic component in it is not 1. It's actually 0.9. Okay, so what we've been calculating as power factor until now was actually displacement power factor. It did not matter. We still called it power factor because all of the circuits that we were looking at, for example, in circuits, all the RLC circuits that we were looking at, they were not distorting the current waveform. The voltages and currents in those circuits were all sinusoidal. Once you start working with currents or voltage waveforms that are not sinusoidal, then the power factor would basically differ from the displacement power factor. So what we have been calculating so far is actually the displacement power factor, which is cosine phi. The power factor, you have to include the harmonic in it. And something that represents the harmonic contamination, which in this case is IS1 over I1. This shows how much of the waveform is actually in the first harmonic. This tells me that 90% of the waveform of this square wave is created just by the first harmonic. That means that when you add all the other frequencies, you only are adding another 10% to it. Okay, so the displacement power factor is 1, the power factor is 0.9. And remember, when you're calculating the power factor, you always have to say lag or lead. Without lag or lead, you get half the point. So this is 0.9 lag, and the reason it's lag because we have a motor as our load. A motor is an inductor, and inductors always create lagging circuits, right? So here we have 90% lag because we have an inductive load. Now, had we had a resistive load and the input current was sinusoidal, then the power factor would have been 1, the displacement power factor would have been 1, and the total harmonic distortion would have been 0. But because we are pulling a square current now, square wave current, we have the power factor being 90% and the THD being 50%. Any questions on this example? Okay. So this was all single phase, right? So the rectifiers that we were looking at were all single phase so far. But in industry, you don't see single phase rectifiers being used often. Instead, you see either three phase or multiple phase. So for example, in aluminum smelters, like the picture that you see here, you can see rectifiers that are 48 phases or 52 phases, something like that. And the reason for that is not only you can get higher powers when you increase the number of phases. So if you have, if you're dealing with, for example, 20 kilowatts, with one phase, the voltage is only, I mean, it can go up to 120, right? 120 volts. Let's just say, for the sake of argument, this is almost 100 volts. The current in this case will be 200 amps. 200 amps is a lot. When you go to 200 kilovolts, you'll end up with 2000 amps for one phase. And this is too much for one phase. The size of the cables, the equipment, I mean, it just basically does not make sense. So instead of one phase, we use three phases. In aluminum smelters, they use up to like 52 phases because the currents involved in their kilns, in their in basically the induction ovens that they use to melt aluminum is quite high, so they need a lot of current. And so they use even more phases than three. So that's why we have something called multi-phase rectifiers. So multi-phase rectifiers not only give you higher powers, but the other thing is that when you increase the number of phases, I mean, for a single phase, we saw that the output would look like this, right? If I change this to 3-phase, then I will get 6 pulses over the same period. And this is already much smoother than this, right? So it's almost flat. So if you were to use a single phase, you can't just use the diode bridge on its own. You have to add a filter on the output. You have to, for example, put a capacitor, then a Zener diode, something to regulate and flatten this curve. But if you use, for example, 3-phase, you get something that is almost flat already. So the filtering or the equipment that you need to use here is less and much cheaper. If instead of 3-phase you use 6-phase, then you get 12 of these. So it'll be even more smoother, right? So that's why we have multi-phase rectifiers. So here's an example of a multi-phase rectifier. This is the secondary of transformer. Yes, Imran.
So like you said, that if we have more phases, then that means that we much on filtering the signal. But like having more phases, does that mean is it cheaper than having more filters?
It's certainly much cheaper on the filter side, yes. So you don't need to spend as much money on the filter. You don't sometimes you don't even need a filter then if you use 3-phase or multiple phase. But if you use single phase, first of all, you not only you can't get as much power through, you also have to spend a lot of money on the filtering. The filter on the output, not the input. The output of the rectifier, right? On the load side. You have to basically, so if this is the waveform that you're getting on the output, you have to filter it to get a flat voltage like that.
So like that means, so having more phases is having single phase because it's cheaper, right?
It's cheaper on the filter, and you can get more power through.
Okay.
So I'm just eating here. So what happens when you add more phases is that you get a waveform, voltage waveforms that look like this. This is like a secondary of a transformer. So depending on how many phases you have, you're creating sinusoidal waveforms that are this much apart. So if you compare this zero crossing with this zero crossing, each sine wave is 2 pi over q radians apart. So for example, if you have 3 phases, you have one phasor here, q will be 3, right? Yeah, one phasor here, one phasor here, one phasor here. So it's like you're dividing the full circle into 3 regions. So each one of them will be 2 pi over 3 or 120 degrees apart. 2 pi is 360. 360 over 3 is 120 degrees. So your phasors will be like that. if you have 6 phases, it means that you're slicing the the pie into what? Into 60 degrees each. So you have 2 of these, right? And so you get these waveforms. Now, if you look, there's one diode attached to each phase, and we have a resistive load on the output, and this is the return. What happens here is that the diode that sees the highest voltage across it will conduct, and the others will not. So when you compare these waveforms, these voltage waveforms, here V1 is the greatest of all the other ones. So in this case, D1 will conduct. And so this, the load will only see V1 across it until here. Then V2 is the greatest. So D2 conducts. And you get V2 here. Then you get V3, V4. So you're only getting the top, right? And that's why you go from this to this. Make sense? Okay. Now, I mean, there are some equations that show you how to calculate the RMS voltage and RMS current. I'm not going to spend much time on this. On the 3-phase, we'll be looking at this in more detail, but you can have a look. With these equations, the good thing is that by changing Q, so you can calculate the RMS voltage and the RMS current for example, 6-phase or 48-phase or 52-phase cases if need be, right? But the thing that I'm more interested on is the 3-phase one. So this is the one that I want to spend more time on, because this is the one that you see more often. So in a lot of cases, especially in industry, I mean, the motors and everything that you have are 3-phase. So with 3-phase, you have 3 waveforms that are sine waves, I mean, that are 120 degrees apart. Remember, you can create a sine wave by spinning a vector around a circle, right? So when you spin a vector around the circle, like this one is giving you a sine wave with a phase angle of 0 degrees. This one is giving you a sine wave with a phase angle of 120 degrees, minus 120, so it's shifted forward. And then the other one, 240, or plus 120. So you get 3 waveforms, sine waves that are 120 degrees apart. Now here I have a transformer that has a primary and secondary side. It's a 3-phase transformer. Okay, so it means that I have, imagine this as 3 power supplies. Sorry, voltage sources, I mean. So imagine this as this. You have 3 voltage sources, and each one of them is sinusoidal. So this one is, for example, VAN with 0 degrees. This one's VBN, sorry, VCN, I mean, 120, and this one's VBN negative 120. And you're using these power supplies to feed a 3-phase rectifier. For those of you who didn't have 251 with me, does this make sense? Can you just imagine this as three parts of the three voltage supplies? Yes, no? The other thing that I can suggest is that if you have access to the book, to the Rashid, if you turn to, I think it was Appendix E. Let me just quickly check. So Appendix E is the Fourier analysis. There's a appendix on three phase. I'll just quickly check it. Yeah, Appendix A. So it's like 1, 2, 3, 4. 4 pages. Actually 5 pages. So if you read those 5 pages, it tells you everything that you need to know about three phase for this course. Okay, so if you did not have 251 yet, please just have a look at the Appendix A that talks about three phase, so that when we are talking about three phase, you know what we are talking about. But generally, it means that you have three voltage sources that have the same magnitude and the same frequency, but their phase angle is 120 degrees apart. That's all it means. Okay, so if I use those, yes, Imran.
Just want to make sure, can we also think it in this way, like we did before? So each coil of primary is inducing current in each coil of secondary, so like 3 phases. Does that make sense? Can we think it in that way?
You can, but then we have different types of wirings, right? So we have the star or Y and delta, but I don't want to get into that. Just think about it. Yeah, so just think about it as 3 voltage sources. So the secondary that you're talking about works like a voltage source, right?
Mm-hmm.
But remember that those 3 voltage sources will end up with 6 terminals. And we only need 3 of those. So the way we connect them here is that we make one common, that's this neutral point, and then we'll take the other 3. We call that a Y connection. Okay, so just think about it as these 3 voltage sources that are 120 degrees apart. And we've connected them like that. Don't worry about the wiring and why we do it this way. Just think about it like these sine waves. So you're getting these sine waves on the rectifier.
Makes sense. And then how do they do it for 52 phases? Is it like the same thing but on a bigger scale?
So the 52 phases will be like this one, right? Like this star. So you'll have 52 of these.
Oh, okay.
This is a bit different because you only have one diode per phase. That's why we call it like a half rectifier. But it does the job. So in places where they need more than 3 phases, they usually use a star configuration like this. But don't worry about that. Was more like general knowledge for you, right? I want to focus on the 3 phase for the time being. Okay, so this is basically the three-phase rectifier. Notice that here we have 6 diodes, so not 3, 6. That's why we call this a full bridge. And these are the waveforms that we are seeing across the diodes. Notice that these are the line voltages. So line voltages means like these 3 voltages that are coming here. The voltage difference between each one of them is called the line voltage, or line to line. Now we use these 3-phase rectifiers in places where we need more than 15. I think this should have been 15. More than 15 kilowatts. Up to 15 you can use single phase, but after that, from 15 to 1 megawatt, you can use 3-phase. Not 1 megawatt, but in the megawatt range. Few megawatts, right? Now, so the diodes here are numbered in order of conduction sequence. That means that the numbers that you see here, 1, 3, 5, 2, 6, 4, this is the sequence that shows which diode comes in first and which one is the next one. So this means that this diode conducts first, then this one, then this, then D4, then D5, then D6, and then the sequence repeats itself. You can see the numbering on top of the waveforms as well, and it kind of starts here. Okay, so it means that first I have D1 and D2 conducting, so that's for this part. Then I have 2 and 3, so 2 and 3. So this stays on, then 3 comes in, then 3, 4, then 4, 5, then 5, 6, and then 6, 1, and then it repeats itself again. The operation principle is the same as before. So whichever voltage is greater, that's the one that is passed on to the load. So here, for example, CB is the greater one. So CB is the one that is passed on to the load. Okay. So you can think of it this way. If like these are the line voltages. So AB means the voltage difference between line A and B. So this is the voltage that is being passed on to the load, right? It says the pair of diodes which are connected between the pair of supply lines having the highest amount of instantaneous line-to-line voltage will conduct. So that means that here I have VAB being the greatest voltage. The 2 diodes that are connected to A and B. So A, D1 is connected to A on the upper side. And if you follow the line for B, D6 is the diode on the lower half that is connected to B. In this cycle, 1 and 6 are conducting. So you get the current from A going this way, going through the load, coming back through D6. So this is basically your circuit, like that. Now, if I imagine this as 2 power supplies, this is negative, positive, negative, positive. I'm going this way, right? Coming back through D6, coming back here. If I write a KVL here, what is the equation that I'm going to get? So this is VAN, this is VBN. Let's write the KVL. So starting from here, I have negative VAN plus V out plus VBN equals 0. If I rearrange this, I have V out equals VAN minus VBN, which is the same as VAB. And that's what you see here, right? And that's what we call a line voltage, because it's the voltage difference between this line and this line. So when you're actually figuring out how long the each diode is staying on, if you draw the phase voltages, so these were the line voltages, but if I draw the phase voltages, it makes it more clear how this thing is working. So the phase voltage is the voltage across, like it's the voltage of each supply on its own. So I have 3 of these supplies, voltage supplies or voltage sources. Whichever is greater is passed on to the load, and whichever is smaller will turn on the bottom half diode. So look at it from here. On the top side, in this case, VAN is the highest for this sequence, right? So from the top, VAN will turn on D1. So here, for this period, D1 will be on. Now comparing this waveform and this waveform, you can see that for this half, which one of these two is the smaller? The red one or the what color is this one? Brown, is it? I'm colorblind, sorry. So is BN smaller or CN smaller for this half? They're the same? Well, this is here, this is here. Which one is smaller? This waveform is smaller, right? This one.
BN.
It's lower than the other one. So for that period, for this period, D6 is on. D6 is the one that is connected to BN. See that? If you follow the B, it means that this is the one that is seeing the smallest negative on its cathode. So the highest voltage on this side is turning on D1. The smallest voltage on this side is turning on D6. So what I'm getting is these D1 and D6 conducting here. But notice that this is 2 halves. The other half, which is this half, is the CN that becomes smaller. So now this is B, this is C, and C is smaller, right? In value. So if you trace C, C is connected to D2. So what that means is that for half of the time that D1 is on, D6 will conduct from the bottom half, from the bottom FET. And for the other half, D2 will conduct, like that. So you get this kind of a sequence. So each diode, like for example, D1, stays on for 120 degrees. For the top part. For the bottom half, each one of these is 60 degrees. right? But in general, each diode essentially, like you can see that this one stays on this half as well, and this one stays on for this half. So it means that D2 stays on here, D6 stays on here. In general, if I ask you how long each diode is conducting, it's conducting for 120 degrees. But they're shifted, right? That means that each of these diodes works with 2 from the bottom. Like this one, D3, works with the other 2. D3 works with D2 and D4. D5 works with D6 and D4. So D4 and D6. And that's basically the sequence. Does that make sense? Okay. Right. Okay, so each diode conducts for 120 degrees, but each one from the top works with 2 from the bottom. So for example, D1, which is this, works with D6 and D2. That means for half of the time that D1 is on, D6 will be on. For the second half, D2 will be on. And if you ever forget, if you could draw these 3-phase voltages, remember that these are phase voltages, not line, right? Because using phase voltage, it makes it easier to analyze the, makes it easier to figure out which diode turns on. So if you draw the phase voltages, whichever diode sees the highest voltage across its anode turns on, and whichever diode sees the smallest voltage across its cathode will turn on. All right, so now that we have this waveform, so this is the output waveform, and where I got the output waveform was that whichever 2 conduct, they put the line voltage across the load. So these are the line voltages that are being passed on to the load. So for example, when D1 and D6 were on, they were passing on VAB to the load. Okay, so here VAB is passed on to the load, and this is the voltage that I'm seeing across my resistive load. When 5 and 6 when 5 and 6 were on, like here, VCB was passed on. So VCB is this voltage. And you can see that it goes through D5, goes through the resistor, comes back through 6. So this is the loop. And you can trace these for the different sequences. So this is essentially my output voltage. Now my goal here is to find the DC value and also find the RMS. Let me just get this sequence right for a second. Okay, so now I want to find the RMS and DC value of this waveform, the output waveform. So I want to know what is the average and what is the RMS. And this part, is the part that needs a bit of attention. So these are phase voltages, equations for the phase voltages. These are the equations for the line voltages. You can see that line voltages are √3 times greater, and they lead by 3 degrees. So for example, the phase was Vm sine omega t. The line will be √3 Vm sine omega t plus 30 degrees. Okay? And remember that it's the line voltage that is being passed on to the load. So as I showed you, for example, for this sequence, 6 and 1, when D1 and D6 was on, you get this loop. And this loop includes two voltages, includes VAN and VBN. When you write the KVL, you're going to see that V out actually equals VAB. So if you take VAN from here, which is this, I'm going to write it in phasor form, and VBN, and you subtract them, you're going to see that you're going to end up with this equation, which when you come back to the time domain is √3 Vm sine omega t plus 30. And we call this the line voltage. And this is what you see here. Okay. Now, first the average. So how do I find the average of a signal, of a periodic signal? The average means that you can take one frame of this waveform, work out what the area will be when you flatten the curve. So if this was a pile of sand and you flatten it, what would be the height that you get? So your book uses these funny equations that are a bit harder to follow. It was hard for me to follow, so I simplified it for you guys. Let's say I want to find the average value of this portion. So the average value will be A over the distance. So the surface area A over the distance, which is 2 pi over 3 minus pi over 3, which is pi over 3. How do I find this area? Well, to find the area, I need to know the equation for this curve. This curve is the same as VAB. And I have the equation for that. But there is one trick. If you look at the origin, it says 0, but we know that this is not 0. I mean, if you follow VAB, you can see that it starts here, but we know that VAB actually starts from 30 degrees, not 0. So that means that these numbers need to be shifted. And this is one part that the book was a bit confusing. So all you need to do is you need to shift those scales, the x-axis or the horizontal axis by p6 degrees. So that means that this is 0 here, and this is, so the distance here is 30 degrees or p over 6. Okay, so this means that this is not p over 3, but it's actually p over 6. So if you subtract 30 degrees from these, you get the correct bounds for the integral. So the area, the formula that I have for VAB, this curve here, is this. And that's the formula that you see here. Because I'm integrating respect to omega t, I've changed everything to radians. So 30 degrees is p over 6. And the bounds for this are p over 6, and this one is p over 2 when you shift. So it's like integrating the surface area from p over 6 to P over 2, and this is your equation. And when you do that, you get the DC value to be this. So the DC value is 1.65 of the peak. So whatever is the peak value, sorry, it's 1.65 times Vm. Vm is the peak of the phase voltage. So and the peak of the line voltage √3 Vm, which is about 1.73. So this is round about here. So the DC value, as expected, is slightly lower. That means that if you flatten this pile of sand, you would expect the height to be around this area, right? So if I give you a three-phase rectifier and a resistive load, and I tell you what is, I know that your output has a bit of a ripple, but if you flatten it somehow, what is the DC value that you get? You're going to say the DC value is this, 1.65 times Vm, and Vm is the peak of your phase voltage. What was the phase voltage? The phase voltage was VAN on those three supplies that was supplying the rectifier. So this is CN, this is VAN. This had an equation, Vm sine omega t. The peak of this supply, voltage supply, is Vm. Now, what about the RMS? How do I calculate the RMS of a curve like this? Well, you have to square it, right? You have to square this waveform because the general formula for RMS is √2 of x squared the theta over t, right? So I have the bounds, I have the equation. All I have done is I have squared this waveform and put it into the equation. So the same distance, pi over 3, but instead of integrating VAB, you have to integrate VAB squared. And when you do that calculation, you get 1.655, slightly more than the DC. So the DC was here, the RMS is slightly higher. Okay, are you still with me?
Yes.
Okay, at least one person is, that's good. So I can write the equation for the output voltage that is like that by using Q equals 6 in the equation that I had from the multi-phase rectifiers, but we don't need this at this time. It's just so that you have an equation for the output voltage. Usually what we are interested in is to know what is the DC voltage. So what is the DC if I flatten this waveform here, what would be the DC value and what would be the effective or RMS value? Okay, so these two. Now, what about the currents? Well, the currents are a bit funnier. So the line currents, these are the currents that are coming out of the transformer or those three voltage sources. So these currents are this. So for example, IA is the current that is coming out of the VAN, this current here, IA. You can see that it conducts for 120 degrees, then it goes the other way around. And when you want to calculate the average or the RMS here, this is the waveform that you have to take into account. If I ask you what is IC or IB, it's going to be the same waveform, but they're going to be 120 degrees shifted. So for example, the waveform for IC will start here. So you get something like this. Right? And the same for the other one. So you get this will be IA, this one will be IC, and so forth. They're going to look like each other, but with 120 degrees, but they'll be 120 degrees apart. Now here, to find the RMS of the current, so RMS of the transformer current, again, remember that you have to shift the scale, the horizontal scale, because this is the 0, not here. This is actually minus P over 6. So you have to change these numbers. But the principle is still the same. You know the formula. So for example, if I tell you what is the RMS, it can calculate the RMS of one of these. And remember that you have 4 of these in one period. So I have 4 over 2 pi. And then the formula that I have for the current, since I have a resistive load, will have the exact same shape as the voltage, but it's over R. Okay, so it's 4 of these over one period. The period is from here to here. So in 2 pi, I have 4 of these surfaces. And so when you calculate the current, you get 0.78 IM, with IM being this. And if you calculate, and so this is the line current, and this is the current that the diode sees. Remember that the diode sees a rectified current, right? Just notice that for the current, for the diode, the period is from here to here. So the period is when the periodic waveform repeats itself. Here you only see 2 of them. So 2 over 2 pi times the same thing, right? 2 over 2 pi. And so the RMS value that the diode sees is going to be half of IM. Now, again, just remember that because our exams are open book, don't worry about memorizing these formulas. You just got to know which formula, like what each formula means and what is giving you and how and where you can use it. That's all you need to know, right? So don't get intimidated. I know that you have a lot of funny shapes and a lot of math in this course, but the good thing is that it's open book. During my time, we had to derive all these formulas in the exam. So you're doing much better than how we were taught these things. Okay, any questions? Can we start our first example? I tell you what, I'll give you, let's take, what is it now, 1:05? Let's take 5-minute break, come back at 1:10, and we're gonna basically look at example 2 and then finish the lecture. Okay? I have silence, so you've already started your break. Okay, see you in 5. Okay. Is everybody back? Okay, good. So let's see if we can put all of those formulas into action. So here I have the same three-phase rectifier supplying a resistive load. It says a three-phase bridge rectifier is fed from a Y-Y transformer. So before I had a delta Y, here the primary is also Y. It won't affect our calculations because everything that we've done so far was on this side. So we weren't looking at the primary, but it's a Y-Y transformer. And it has a pure resistive load R. The rectifier delivers 60 amps. So the current here, so that current that we had, the current through, sorry, the output current. I'm looking at the input current. This is the output voltage. And since I have a resistor as my load, my output current is going to look the same. And the DC value of this output current is 60 amps. And the DC value of the output voltage, or the average of it, if you like, is 280.7. The source frequency is 60. So what is this 60 giving you? It's giving you omega. Okay, so these are the information that we have. Now we are asked to find the efficiency. What was FF? Anybody? Does anybody remember what it was? The form factor, very good. The form factor, the ripple factor, the transformer utilization factor, the input power factor. So the input is at this side. What is PIV?
Peak inverse voltage.
Peak inverse voltage. So the maximum inverse voltage that each diode sees, because in the next stage where we have to actually design these things, when you're using two monitors, it's hard to get your mouse across. Yeah, so when you are when we are designing these rectifiers, we need to be able to select the right diodes for the application. So we need to know what is the peak inverse voltage that the diodes will be experiencing, so that we pick diodes that could bear that inverse voltage. And then also the peak current through the diodes. Okay, I'm hoping that we could at least get half of this done today. So what is the efficiency? Remember that the efficiency was not the actual performance, the actual power efficiency, but it was the performance efficiency of the rectifier. So it was one of those measures that shows how well this rectifier is rectifying. And the way we calculate the efficiency is by calculating the output DC power over the output AC power. Now, because we have a resistive load, for a resistor, if you know the voltage across it, the power that it's consuming will be V squared over R. Now the DC one will be simply VDC squared over R, right? The AC power is VRMS squared over R. So we looked at an example in the previous lecture where we had a waveform that looked like this. It had a DC value and AC and an RMS. PAC means that you have to use the RMS voltage. So this should have been RMS. So that means that we have to calculate the DC and the RMS voltages. So you have the formula for DC. The DC voltage is 1.654 VM. What is VM? It's the peak of this voltage. So if this is VAN, it's a sine wave that will have a peak voltage, right? That's giving me the peak of the input voltage. And VRMS is 1.655 VM. So we are actually given VDC. It's 280.7. But I mean, we don't even need that, because if you write everything in terms of VM, you're going to have 1.654 VM for VDC, and for VRMS, you're going to have 1.655 VM. So the two VMs cross out. Remember that this is squared because it's power. So we can calculate the efficiency, and the efficiency turns out to be 99.83%. So it's really good compared to what we had before for the single phase. I think for the single phase, it was down in the 80s, if I'm not mistaken, the efficiency. This is doing a really good job in rectifying the input, the AC input. So the efficiency, the rectification efficiency is 99.8%. Now, the form factor, the formula that we had for it was VRMS over VDC. So this is the formula that we drive for the output RMS voltage. This is the formula that we drive for the output DC voltage. All you need to just plug in these values, right? So the form factor is almost 1. Remember, form factor, it could be 100, sorry, it could be 1 or more. Ripple factor could be 0 or more. So DC, AC, RMS. So the form factor is DC over RMS. Now, the ripple factor is, I mean, the formula that we had for it was this. It was actually AC over DC, if I'm not mistaken. But since we already have this, we can calculate the ripple factor, and it's 4%. That means that this voltage that we get, 96% of it is this base. Only 4% of it is the ripple, which makes sense from the image that we have, right? So these were the easy stuff. Now let's look at some of the harder stuff. So the transformer utilization factor. So how do you find the transformer utilization factor? So the transformer utilization factor is the DC voltage, sorry, the DC power over the volt ampere, or the apparent power of the transformer. Now, for a three-phase transformer, the apparent power is 3 times of each phase's apparent power, right? So it's 3 times the magnitude or the RMS of the phase voltage times the RMS of the phase current. Let's work on some of these. So the phase voltage is the Vs that we found, which is the peak over √2. The peak of the phase voltage over √2. I phase, so the phase current, because this is a Y, is the same as the line current, and we found the I line as 0.78 IM. That was another of those formulas that we found. So this was the waveform that we had for the line, and we found the RMS, right, for this. And the maximum current, because we have a resistive load, is the peak of the line voltage over R. So combine all these formulas, we get the apparent power of the transformer being 3 times the phase voltage. So these are RMS, just remember that these are RMS. Times the RMS of the line current, both in terms of VM. And PDC, we already found it before, so PDC is VDC squared over R. I can write VDC in terms of VM, so that the VM on top, VM at the bottom, and the R's cross out, and you get 95% 0.4 utilization of the transformer. So that means that because the output contains a bit of DC, they're going to end up with saturating the transformer a bit, but it's not going to be much. So if you were to select a transformer for this application, you have to upsize it by a few percent. So whatever is 1.95, you have to upsize it by about this much, so that even when the core saturates, you still get the power rating that you want. Okay, so what's 1 over 95%? So about 5%. So whatever is the power rating, you have to add at least another 5% to it. Usually, but we do much more over design than this. So we might add 25 or 50% to the power rating, just to be on the safe side. Okay. So that's the transformer utilization factor. Now it says the input power factor. So for the input power factor, that's on this side. I need to know what is the input power and the apparent power of the transformer. So the apparent power is what I just found. For these transformers, because the efficiency is usually, like the power efficiency of a transformer is usually above 96%. We're going to assume it to be 100%. So we're going to assume that the transformer itself is not losing much power. So that's why I'm going to assume that the P in is the same as the P out. Okay, and these diodes are ideal as well. They don't have a resistance, so they're not dropping the efficiency at all. So what we are basically saying here is that whatever is this power because we are assuming the transformer and the rectifier to be 100% efficient, is the power that you need to put in. So P in is the same as P out. Now P out is your AC voltage, so RMS times IRMS, because it needs to contain both the DC and AC components of the voltage, right? So we found the apparent power of the transformer before in terms of VM. I can also find the PAC. So PAC, or the power here in terms of VM, is VRMS squared over R, and I know the formula for VRMS. VRMS is 1.655 VM squared over R. So if you do the division, you get the power factor to be 95.6%. That basically tells you how much reactive power this takes. Okay, so the only assumption here was that we are assuming the transformer and the rectifier to be 100% efficient. But we know that that's not true. Usually this is about 96% efficient, and this one's only, these ones, the diodes have a resistance, so they're also about 92% efficient. So you will end up with the power factor that is lower than this in practice. But for the time being, this is what we're going to see. The peak inverse of each diode, sorry, and this is lag because the transformer is an inductor. So you essentially have an RL load. And the peak inverse voltage that each diode sees is the peak of the line-to-line voltage. I mean, you could see that in the KVL. So if you write a KVL, so you have to write, yeah, so if you write a KVL here, you can see that when these are off, if these switches are off, the voltage that they'll see across them will be this voltage here. So the maximum voltage that they'll see across them will be the peak of the line-to-line voltage. So to go from phase to line, you multiply by √3. These are RMS. To go from RMS to peak, you multiply by √2. Okay. So this was the formula that we had, and we were already given the DC voltage. It was 280.7. That way we could find the peak of the phase voltage from this formula. The peak of the phase voltage is 169.7. To go from phase to line, you have to multiply this by √3. So the peak of the line voltage will be about 294 volts minus this, right? So this is the maximum voltage that any of these diodes will experience. And I'm going to stop here because for the current through the diode, we need to basically discuss it a bit. So I'm going to leave that for our next class. Thanks for staying behind. I know that we went over, but thanks for staying behind. If you have any questions, remain on the line, and then I can basically answer your question. If you don't have any questions, have a great day. See you guys on Thursday.